Welcome, everyone. My name is Kate Rod, and I'm a program specialist at CPAESS. This position affords me the pleasure of working with our wonderful postdoctoral and doctoral fellows. I'm delighted to have you attend the CPAESS Discovery Seminar Series. CPAESS scientists do everything from exploring the ocean depths to flying into hurricanes to having heliophysicists model coronal mass ejections, and we have those who unravel the mysteries of the Arctic. We want to share this with the public, the NCAR-UCAR community, and with our many colleagues at universities and agencies around the globe. Just to orient you, we're going to be using Slido, so you can pose questions for our speaker. You'll be able to find access in a tab at the top left of the screen. It is my sincere pleasure today to introduce you to today's speaker, Dr. Robert Jarolim, who is a NASA Jack Eddy postdoctoral fellow researching at NCAR's High Altitude Observatory in Boulder, Colorado. He completed his PhD in 2023 at the University of Graz in Austria and received the ESPD Patricia Edwin Award, the PhD prize of the International Astronomical Union, and the Josef Kreiner Promotional Award for his thesis. With a background in physics and computer science, Robert has contributed to the field of AI in solar physics, particularly in the areas of automatic feature detection, solar image enhancement, and data-driven simulations. His research topics include coronal holes, solar flares, coronal mass ejections, and ground-based solar observations. His recent publications focus on the use of physics-informed neural networks for magnetic field simulations and tomographic reconstructions of the solar atmosphere. Today, Robert Jarolim will be speaking on disentangling warming and circulation influences on precipitation under global warming. Robert, the floor is yours.
Hello. Yeah, thank you for the kind introduction, and thank you everyone for joining in. So for today's presentation, I want to talk about AI applications in solar physics, and in particular how we can use this synergy of AI and our understanding of the underlying physics to learn more about our closest star, the Sun. So in particular, I want to talk about physics-informed neural networks, and I will give you first a brief introduction about solar physics, and then we'll go into more detail about what are physics-informed neural networks. And then later we'll show you the primary applications where we use physics-informed neural networks for solar physics. So let's get right started. So for solar physics, the basic question is, why do we study the Sun? So first of all, the Sun is our closest star. So this provides us basically with a unique opportunity to study a star up close and relate this star also to other stars. In particular, the Sun is the only star where we can actually resolve spatial details in a greater resolution. And we can study plasma under extreme conditions. So this wouldn't be possible in a laboratory to study plasma on that scale with such an amount of magnetism involved. So the Sun provides us basically here with a unique experiment up close that we can examine from Earth. From the other perspective, the solar magnetic field is the dominant force in our heliosphere. So it shapes the entire solar atmosphere and the entire heliosphere throughout. So this also means that when we look at the Sun and the Earth as a system, those are not two separate entities, but it's more a coupled system. So this means if there are high energetic events happening on the Sun, this can have immediate consequences for us here on Earth. So in order to better understand how the Sun influences the environment here on Earth, it's also important to better understand how these high energetic events build up and how they occur and what their potential impact on Earth is. So how do we do this? How do we study the Sun? The way that we do this is usually with remote sensing observations. So this is like one of the primary sources where we obtain images of the Sun, where we study different layers by using different filter bands, which gives us information about the different layers of the solar atmosphere. So down here, you can basically see like individual slices extracted from different layers of the solar atmosphere, where we have at the bottom the photosphere, including the magnetic field that we measure at the photospheric level. Then we have the chromosphere, which is the layer above the photosphere. And the top layer is the solar corona, which is shown here in extreme ultraviolet. And we can see that this basically rapidly changes when we view different layers of the sun. And in particular, when we look at these extreme ultraviolet emissions, we can see a lot of structure that is going on, which is primarily dominated because of the magnetic field of the sun, which structures this atmosphere. So in particular, we can see various different features. We can see coral holes, we can see filament structures, and we can also see very impulsive events like solar flares and the corresponding ejection of mass, which is called coronal mass ejections. So in order to study this phenomena, we can use these observations. But there's a downside, because what we obtain in terms of the observations that we have is only a fraction of the complete picture of the sun. So we only extract certain layers, and we only have mostly imaging data available. So a complete picture of the sun is actually missing. But what we actually would need is a 3D, like a complete 3D picture of the plasma distribution in the entire solar atmosphere to better understand and quantify these phenomena. So the second aspect of this presentation is related to a novel approach using AI methods. And the primary driver for the recent trends of artificial intelligence are so-called neural networks, which is the primary model that is used for AI applications. So neural networks are like a subfield of machine learning. And the aspect here is relatively simple if we break it down. So here we basically always use a certain input and output data set. And then we try to find a corresponding mapping function, which can generically map from a certain input to corresponding output. So for classical machine learning approaches, there are relatively easy mapping functions used that map from the input to the corresponding output. But in the last recent years, neural networks became more popular. So neural networks are composed of these small units, which are shown down here, which are called neurons. So this basically gives us one free parameter to adjust for our mapping function. But by using like more complex mappings and stacking these neurons together into a network, which is called a neural network, we can basically create arbitrary complex function approximations. And with this, we can also solve arbitrary complex problems, as long as we have a corresponding set of input and output pairs. So this is really the primary aspect that I want to emphasize here, is that we can use neural networks as a general function approximator that can incorporate a lot of information and can solve very complex problems. Right. So most of the recent applications that we have seen of artificial intelligence are all in this regime here, like large language models or image classification tasks or image transformation tasks are all situated in this regime to the far right here, where we have a large amount of data available, but very little understanding of the underlying physics. So while this is like frequently a good approach, and we've seen the success of these applications in the past, for science, we frequently face the problem that we actually want to learn more about the underlying data. So this corresponds to this regime on the far left-hand side, where we have actually like very limited data available, but we have a full understanding of the underlying physics. So here is basically the place that I want to highlight for this presentation, and where we can use the synergy between physics and AI to learn more about our data. So especially in the cases where there's no big data available and we have this knowledge about the physical equations, we can use physics-informed machine learning methods to learn more about our data through the underlying physics. And for this presentation, I want to jump right into the individual applications, and we'll tell you more about how this actually works in practice by looking at specific applications for solar physics. And in particular, I want to highlight two primary fields, basically, where the first one is the application to magnetic field modeling, and the second aspect is for tomographic reconstructions. So we'll talk about first about magnetic field extrapolations and solar magnetic field in general. And for the second part, I will talk about atmospheric, like how we can reconstruct the solar atmosphere from a limited number of viewpoints. So let's get started with the first part, which is about nonlinear force free extrapolations, or in other words, magnetic field modeling. So when we look at the sun in white light observations, what we see is basically just this, the disk and the corresponding sunspots. So sunspots correspond to regions where we have strong fields piercing through the photosphere, and the imprint that we see is this dark structure. When we look at this in more detail, we can see basically that it is this magnetic field which structures these regions and dominates these regions, especially in sunspots, but also everywhere else in the sun. So it's the omnipresent component of the sun is its magnetic field, which determines the entire structure of the atmosphere and the heliosphere. And we can see this more prominently when we mask out the bright solar disk and only view the plasma that is streaming outwards in terms of in the form of the solar wind. We can see that this basically gives us an outline of the magnetic field structure of the sun. So when we focus onto smaller regions where we have strong magnetic fluxes emerging, they look like this here on the right-hand side, so-called active regions. And the primary problem that we have is, again, the limitation of observations that we have available. Because when we compare those two observations here, so on the right-hand side is the magnetic field that we obtain from the photosphere, and on the left-hand side is an EOV observation, which gives us, which images basically the solar corona. We can see that there is a lot of dynamics. A lot of dynamics are happening in the higher solar atmosphere, while we see very little changes in the photosphere, in the photospheric magnetic field. However, those measurements of the magnetic field from the photospheric magnetic field are the primary observable that we have, while we typically can't obtain magnetic field measurements from higher atmospheric layers, or not on a regular basis. But in order to understand how these dynamics evolve, how energy is being built up and released in the solar atmosphere, it is important to understand the full three-dimensional structure of the magnetic field. And for this reason, typically to fill this gap, magnetic field modeling is applied. And in particular, I want to talk here about the application of nonlinear force-free modeling. So the goal here is basically to use this additional understanding of the physical equations together with the observations to estimate the magnetic field in a given volume. So for this, we basically solve a boundary value problem where we have the measured vector magnetograms from the photosphere and the system of partial coupled differential equations in the form of the divergence-free and force-free equation. So how can we use now physics-informed neural networks for this task to estimate this, the magnetic structure in a three-dimensional volume only based on the bottom layer? And this is the approach that we took for this is to use this physics-informed neural network and to use this concept of having a generic function approximation to basically provide an approximation of the magnetic field itself in a certain volume. So let's have a closer look at how this works. On the left-hand side, you can see how this, the principal task that we are trying to solve. So we have our three-dimensional 3D volume, and we have the measurement from the bottom layer. And the goal is to estimate the magnetic field in the entire simulation volume. For this, we use a physics-informed neural network, which serves as a representation of this volume. This means that the network maps at each point in terms of x, y, and z, the corresponding coordinates to the respective magnetic field vectors at this location. We can then train this network and adjust the parameters to match the observations by taking points from the bottom boundary in terms of x, y, and the lowest layer, so 0, as an input and map them to the corresponding vectors. We can then immediately update the neural network to match our observations. But on the other hand, we also want to estimate the field in the remaining volume. And we do this by solving the system of partial coupled differential equations. So when we look at this representation, we can see that this is basically a function approximation. What we can do for this is we can compute immediately derivatives of the output magnetic field vectors with respect to the input coordinates from this representation. So we basically sample random points from within the volume, pass them through the neural network, and compute the derivatives of the outputs with respect to the input coordinates. From this, we can then reconstruct, or construct the partial differential equations and minimize the residuals. So we optimize for those physical equations. And by simultaneously optimizing for our physical model in terms of the partial differential equations and for the boundary condition, we can find a solution in this three-dimensional volume for this magnetic field that is in agreement with both our physical model and the boundary condition. So as a first step, we compare this to an analytical solution just to test if this is a good approximation or if this method actually works. So we use an analytical field solution based on a standard data set, which is used for comparison methods. And specifically, we used this one from Schreiber et al., where they compared 6 different methods for this analytical case. So we take this magnetic field and only extract the boundary from this analytical solution. And then we perform our physics-informed neural network extrapolation with this method. And as you can see, the magnetic field that we get as a solution is very similar to the reference field. And in particular, when we compare this to all the other 6 methods that were used in this comparison study, we can see that this approach provides the best results. With this, we can also move forward and apply this to actual observations. So this is what you can see at the top is at the bottom, you can see the magnetic field, which was used as an input. And the magnetic field line traces here, which are those lines, outline basically the magnetic field that is reconstructed, that is extrapolated from this measurement. At the bottom, you can see observations in extreme ultraviolet, which outline the magnetic field structure. And you can see that the overall topology matches well. And we can also see that highly twisted fields appear as these bright structures in the observations, both in pink here and in black. And we can also see that this approach is capable of capturing this eruptive structure, which is shown here in green, which becomes visible shortly before a flare eruption. But just a single frame is typically not enough to understand the full energy buildup and release processes that are happening. And this is really where the strength of this approach comes in, where we can use this in a computationally efficient way to extrapolate long time sequence. So what we do here is we use a series of magnetic field measurements from the photosphere and perform extrapolations of those measurements over 5 consecutive days at the full instrumental cadence of 12 minutes. So it's a large number of individual extrapolations that need to be performed. But what we can do with this approach is we can start by extrapolating the first frame in the sequence, and then we can use this already existing solution to change the boundary condition and converge to the next solution. And this is a very efficient way of converging to new solutions over time. And this enabled us to compute this full evolution of 5 days in less than 10 hours of total computing time, providing us with basically extrapolations in quasi-real time. So this allows us then to use this time sequence and to study how the energy evolves over time, how the energy is being built up, and how the energy is being released. And this is what you can see here on the right-hand side, where we have the corresponding computed magnetic energy, the free magnetic energy, and the magnetic helicity in this volume over time. So this ranges over the full 5 days period. And as you can see, the bottom panel shows the corresponding ghost flux, which is an indicator for flare events. So we see those sharp spikes in intensity here, which corresponds to flare events. And when we look at this largest flare here, which is an X-class flare, so a huge energy release, we can see that this is also reflected by our model result, where we can see this sharp cut in magnetic energy, and we see this sharp transition and energy release process that is associated with this flare event. So in that sense, this model captures the actual dynamics that are happening in the solar atmosphere in terms of how energy is being stored and energy is being released. So we can also, since we have a full three-dimensional reconstruction of the magnetic field, we can examine this in more detail. So for example, for this prior M-class flare, we can compare the site of energy release with, again, extreme ultraviolet observations of the solar corona. And we can see that this brightness increase where we see here this flare occurring nicely aligns with the energy release site. But this approach is in line with previous methods. It's a different approach to solving the same underlying problem of estimating the three-dimensional magnetic field with the same equations and the same observational data. But we wanted to go further and actually make more use out of the flexibility of physics-informed neural networks to incorporate additional data sets. And this is the second part here, where we extend this approach forward to include additional observational data into the extrapolations to obtain a better magnetic field estimate. So what we want to use here is additional chromospheric magnetic field measurements, which are not available on a regular basis, but we partially have a few chromospheric magnetic field observations that can be used for those extrapolations. The problem that we have, however, with chromospheric magnetic field measurements is that in contrast to photospheric measurements, it can't be assigned to a single height surface. So in fact, they are highly corrugated surfaces where we can't really determine the height distribution in the observations just from the 2D images. So in order to actually use this data, what we need to do is we need to account for this additional height variation in the observations. And here we use an additional approach to use this flexibility of physics-informed neural networks to better incorporate this data. So you can basically see the starting point that we have is now different. Instead of having, so the aim is the same. We want to estimate the three-dimensional magnetic field in the simulation volume, but the starting point is different. So we have, instead of only a photospheric magnetic field measurement, we have measurements from two height surfaces, both from the photosphere and from the chromosphere. So here we introduce an additional physics-informed neural network, or a mapping model, which basically takes as an input the spatial location in terms of X, Y, and Z, and remaps this height surface to a corrugated surface. We can then use this corrugated surface as an input to our previous network, which performs the corresponding extrapolation, both satisfying this, or both optimizing for this physical model and for the boundary condition, which is now the corrugated boundary condition. So the interesting aspect about this is that this approach is basically performed end-to-end. This means that this remapping of the height surface is informed by the magnetic field extrapolation. So the height mapping is assigned in agreement with the magnetic field that is being extrapolated. And on the other hand, this additional information of the chromospheric magnetic field changes the extrapolation itself. So by iteratively performing this approach in a combined way, we obtain a magnetic field solution that incorporates both the observations from the chromospheric field and from the photospheric magnetic field. So what we do again here is to use first synthetic data, where we can fully quantify if this approach provides an improvement. And for this, we use a simulated magnetic field from a Murim simulation and extract slides with the three different corrugated surfaces from the chromosphere and from the photosphere. So this is shown here on the left-hand side. So this is the input that the model receives at three different heights. And in the central column, you can see the actual height distribution. And as you can see, this ranges by multiple megameters in height. So it's a significant variation in terms of height, ranging basically from the photospheric level up to 20 megameters in height, going almost up to the, reaching even up into the corona, what we have in terms of the measurements here. So when we apply our approach to this, we can then extract the remapped height surface, which is shown here on the right-hand side. And here we can see that this is in close agreement with the actual ground truth. And what I want to highlight here is that the only information that this model gets is the magnetic field that is shown on the left-hand side, while the central column is completely hidden, but still we obtain a correct reconstruction of this height variation. And most importantly here is that when we use more observations, when we compare this to the actual ground truth magnetic field, we always obtain better solutions when we use additional information of this magnetic field. So we can then use this again to apply this to observations, where we can actually study the solar features in more detail and to see how this method performs for this scenario. So here you can see an observation of the chromosphere as observed in H alpha. And what you can see here is this active region, and here's this elongated dark structure, which is a solar filament, an active region filament. So when we use only the photospheric magnetic field as an input here for the extrapolation, what we obtain is a magnetic field structure that looks similar to, that looks like this. And this would suggest a different topology where we obtain a less twisted field and less energetic field for the single height extrapolation. But by including additional observations of the chromospheric magnetic field from the Swedish Solar Telescope, we obtain a very different image where we see that we obtain a much more twisted magnetic field structure, which captures much more energy and is in much closer resemblance with the actual observations that we obtain. So this truly highlights the importance of additional observational constraints and to fit them into a coherent extrapolation result. So as a last part for the magnetic fields modeling, I just want to show like the next step that we're working on and where we want to use basically this aspect of memory efficiency of physically informed neural networks. So here we can basically just use the same approach as before and apply this not only to a single small active region, but we can apply this to the whole sun to the whole observed magnetic field of the sun, and to form an extrapolation which gives us a full three-dimensional image of the magnetic field of the global magnetic field. And this is the result of the extrapolation. So we take this magnetic field as an input, and then we perform the extrapolation, and what you can see here are the corresponding field line plots. And when we compare this to the observation in extreme ultraviolet of the solar corona, we can compare the magnetic field topology that we observe in our field line traces to the one that we see in the observations. And when we compare this in terms of the flux ropes, we can see that we have here highly twisted fields, which are in agreement with these filament channels. We can also see that we obtain these highly twisted fields, which correspond to active region filaments, or active region twisted flux ropes. And we can also see that this model reproduces open magnetic field regions like this, this coronal hole at the center of the observation. And this also is true for more difficult regions like the solar poles, where we also obtain here, in agreement with the open magnetic fields at the solar poles, open magnetic field topologies in our extrapolations. So the interesting aspect here as well is that we can, especially in terms of space weather aspects, is that we can monitor now on a global scale the distribution of magnetic energy and magnetic flux, which gives us more information about the structures and where large amounts of energy are being deposited. So with this, I want to transition to the second topic, where we try to address the limitations of viewpoints and the limitations of having a full three-dimensional image, not only of the magnetic field, but also in terms of the plasma distribution in the solar atmosphere. So let's have a closer look at what the actual problem is that we are facing here. So in contrast to observations from like here on Earth, ground-based or like observations that we obtain from real-world objects. For the solar case, we are not observing dense objects, but what we are observing is optically thin plasma, or even like an optically thin emitting plasma. So it is very difficult to determine an exact point because we are not looking at the dense surface, but we're looking basically through the entire heliosphere. And this is we can see this most prominently when we look at these coronagraph observations of white light, where we basically look through the entire heliosphere, and it makes it really difficult to estimate in which direction this mass ejection is actually going. So what we have to deal with is basically projection effects, the line of sight integration, and we also face frequently different spectral bands. So it's very counterintuitive for humans to interpret this data. So what we need is more advanced methods that can combine these data products or like combine multiple observations into a coherent picture of the three-dimensional distribution of plasma in the solar atmosphere and heliosphere. So let's have a closer look how this, what we have in terms of our observing capabilities. So this is how we viewed the sun in the past with 3 satellites. So this was, so those are like, this is like one of the maximum amount of individual observations that we have obtained from different viewpoints at different separation angles. And for this, we only had 3 separate viewpoints of the sun. And most importantly, all of these observations were obtained from the ecliptic plane. So this means we actually have no direct observations of the solar poles, for example. However, if we want to better understand the structure of the sun, its impact on Earth, its impact on other planets, and also its relation to other stars, it is important that we have a full 3-dimensional understanding of our closest star. So how can we address this issue? Of course, a solution would be to just launch new satellites and actually perform these observations. But this would be very expensive, and we don't have this available right now. So what we propose is that we use instead our existing observing capabilities to obtain a 3D reconstruction and then basically create virtual instruments that we can place at arbitrary points in the solar, around the sun to reconstruct these or to estimate these observations. And we can use these virtual observations or virtual instruments not only in the ecliptic plane, but we can also place them out of the ecliptic, viewing the sun from all different angles. So how do we actually do this, and how do we use AI methods for this application? So the way that we address this is with a method which is called neural radiance fields, which was originally developed for real-world objects, for reconstructing 3D objects or 3D scenes from images at multiple different viewpoints. So this was initially designed for real-world objects, and here we basically extend this approach and incorporate the actual physics of the sun using radiative transfer and accounting for the emitting and absorbing plasma in the solar atmosphere. So the basic concept here is a ray tracing approach. What this means is that we have observations at different locations in the heliosphere. So what we can do is we can take these observations and cast rays through the individual pixels into our simulation volume. So here we can make, again, use of this concept of having a neural representation or physics-informed neural network, basically, which performs a mapping from the coordinate space to the corresponding physical quantities. So in our case, the network serves as a representation of the solar atmosphere, which maps coordinate points in terms of x, y, z, and the time evolution t to the corresponding emission and absorption at the respective points. So when we cast our ray into the simulation volume and essentially probe this atmosphere, we get sampling points along the ray. So we take the sampling points, pass them through the neural network, which provides us with the emission and absorption values, from which we reconstruct the emission and absorption profiles. And by using a radiative transfer approach, we can combine this into the predicted pixel value. So of course, in the first iteration, like since we have no information about the actual emission and absorption here, we need to reconstruct this. But we don't have these measurements of the spatial location of emission absorption values. But what we have instead is the actual pixel value from our observation where we started our tracing. So by using this ground truth value and comparing this to our prediction, we can go back to this neural network and adjust our parameters such that this matches this observed pixel value. And by doing this not only for a single observation, but for multiple observations and their temporal evolution, we can then obtain a three-dimensional representation of the sun, which is in agreement with all of those observations simultaneously. So we trace basically this volume from multiple different angles and try to reconstruct the full emission and absorption profile, which then gives us our full three-dimensional reconstruction. Okay, let's try to say this like in a more simplified way. So what we're trying to do is we try to use a ray tracing approach for a single example, for a single observing sequence of multiple observers, where we use multi-viewpoint satellite data and combine this into using neural radiance fields into a three-dimensional representation plus its temporal evolution of the solar atmosphere. Once we have this three-dimensional representation, we can then use it to render novel perspectives. So we can basically place observers at arbitrary angles and create synthetic observations from this three-dimensional representation. The important thing to note here is that what we obtain is only based on the physics, the physical equations that go in and the observations that we have for this reconstruction. So this means we need to fit this for every observing sequence that we want to investigate. But this also means it's not a generative approach where we synthesize arbitrary data, but this is solely based on the observational data that goes into this reconstruction. So now we can apply this to observational data. And this is the constellation that we were using with the 3 satellites over a full solar rotation, where we have observations from those 3 different viewpoints. And by performing this reconstruction, we can then render arbitrary new viewpoints, both in the ecliptic plane, but also out of the ecliptic plane, basically giving us new observations at higher latitudes, even of the poles. And since we also model the temporal evolution, we can even see solar eruptions happening in 3 dimensions. So this is also what you can see here at the end of the video, where you can see this large-scale filament eruption, which is happening and is also captured in this 3-dimensional reconstruction of the solar atmosphere. So the most interesting aspect about this is that this basically gives us a, so to say, first look at the solar South Pole. So typically, all of our observations are obtained, remote sensing observations are obtained from the ecliptic plane. But here we can actually reconstruct, based on our existing observing capabilities, a first estimated view of the solar poles. And this is what you can see here at the center, which is directly the view onto the pole. But how do we actually achieve this? Because we don't have direct observations of the pole. But when we look back at our input observations, we can see that since this is an extended solar atmosphere, we are still probing this region from highly inclined viewpoints. So although we don't have direct like lower or higher latitude observations, we still have viewpoints of this polar region. And in addition, we have a full temporal evolution, which basically gives us a more complete scan of the entire sun. So this is what you can basically see here, which each arrow corresponds to one observation in red, green, and blue, based on the individual input observations. And this color change shows you the temporal evolution. So you can basically see here all of those observations that go into this single 3D reconstruction in order to obtain this viewpoint. And we can do this for a single wavelength channel, but we can also do this for multiple different, various different wavelength channels, as seen here. But again, since this is since we obtain a full 3-dimensional picture of this, we can not only reconstruct individual new viewpoints, but we can actually examine the solar atmosphere in more detail. Or we can basically probe individual slices of the solar atmosphere and look at the spatial distribution of the plasma in the solar atmosphere. So this is what we're trying to do here. So on the left-hand side, you can see this is an actual observation from stereo B. And this red slice here is the slice of interest. So we can immediately use our approach here to basically generate the corresponding view from the side, where this red line now intersects with the limb of the sun. And since we have this three-dimensional representation, we can immediately extract a slice of this atmosphere. And this is what you can see up here. And when we look back at the slice that we have extracted, we can see that we have here this solar active region, which appears bright in the solar atmosphere and is well rooted in the photosphere. And we can also see other features like this coronal hole, which appears dark. And we can see this correspondingly here in our reconstruction, where this corresponds to a density decrease all the way down to the photosphere. And in contrast to this, we also have this dark feature down here, which is a solar filament, where we can see that this is represented as a dark cavity suspended in the solar atmosphere. So we can actually examine those individual features now in more detail and examine their three-dimensional structure. Since we also capture time with this approach, we can use this to better study how coronal mass ejections are occurring and how they evolve, and in particular in which direction they are ejected, which is of primary interest when we think about space weather aspects and to see if this ejected plasma can have an impact on Earth. So what you can see here is a reconstruction of a viewpoint based on two observers, so two observing viewpoints. And since we have this three-dimensional information, we can also extract the corresponding height and the integrated absorption from these observations. So let me play this video here. So you can see that this dark filament here lifts off and is being ejected. And we can see this corresponding energy release in terms of a flare, where we see these flare ribbons lower in the solar atmosphere. So now we can use our approach to fully reconstruct this and to actually map the corresponding height distribution. So what we see here is basically a tracing of the individual points that we're observing in terms of height. So we can actually map this to the corresponding height surface. And from this, we can see that this plasma is ejected outwards. And then we can also see that these flare ribbons are all mapped down into in the solar chromosphere. We can also use this to estimate the integrated absorption. So this corresponds basically to the dense plasma that is suspended in the solar atmosphere. And here we can also see how this plasma is being accelerated and ejected outwards. So this basically gives us also the opportunity to extract slices from this and to compare this in more detail. So at the top, you can see the corresponding emission, and at the bottom, you can see the corresponding absorption, which is reconstructed by our approach. And here you can see basically how this emitting plasma is ejected outwards, both in the emission and in the absorption. And then we can also see how these flare loops are formed lower down in the solar atmosphere. So this gives us a new way of studying these events in a reprojected form without relying on just images, but by actually obtaining a three-dimensional image of this temporal evolution. So one part that we are working on right now, which is here just an outlook, is to extend this forward. And instead of using emission and absorption values, what we are trying to do is to use density and temperature estimates of the solar atmosphere instead. So we're trying to reconstruct those observations by actually modeling the density and temperature distribution, and then using the instrumental response function to obtain those images. So then with this, we can basically use multiple channels simultaneously, integrate all of this data into a coherent three-dimensional representation of the solar atmosphere. So what you can see here is at the central part here, the region of interest, which already shows the reconstruction by our approach. And this black dashed line is the line that we're interested in. So it's similar to before. We can basically examine the distribution of plasma in the solar atmosphere in more detail. So from this we can see, directly map coronal hole boundaries. We can study solar features without projection effects, and examine them in more detail. So let me just conclude with this last outlook here, which is basically where we are planning to go with this. So what we're trying to do is to extend this to more applications, but most importantly, to integrate them together. So in particular, using what I was introducing in terms of magnetic field extrapolations and in terms of tomographic reconstructions or 3D reconstructions of the solar atmosphere into a coherent picture, which takes the information from both measurements and combines them into a more coherent picture of the solar atmosphere. So at the moment, we're working on different magnetic field modeling at different complexities. We're also working on tracing these tomographic reconstructions further outwards to better observe coronal mass ejections. We are also using this to reconstruct magnetic field measurements in terms of spectropolarimetric inversions. And as already said, we are trying to integrate all of these approaches together into one coherent modeling approach of the sun. So in summary, I hope I was able to show you this great synergy that we have between physics-informed artificial intelligence and the use of our physical understanding of the underlying systems to learn more about about the data and about the sun. I hope I was able to show you that PINS provides truly a state-of-the-art data-driven simulation approach. And in particular for the magnetic field applications, this approach is able to achieve first real-time magnetic field extrapolation, which is critical for space weather forecasting and monitoring energy and release processes in the solar atmosphere. The approaches physics-informed neural networks are in particular flexible in terms of their input. They can be easily extended to larger simulation volumes, and they can also incorporate additional measurements, like for example, the chromospheric magnetic field measurements. We can also use this approach for tracing in terms of 3D reconstructions, where we can use radiance fields to obtain a tomographic reconstruction, 3D reconstruction of the solar atmosphere. The important aspect here is really that this approach provides us with new opportunities where we can leverage more observational data and advance to more advanced simulations to obtain a better understanding of our closest star, the sun. With this, I would like to say thank you for your attention, and I'm looking forward to your questions.
Robert, thank you so much for sharing your work. We really appreciate it. Now we'll begin our question and answer portion of today's seminar. I'd like to direct everyone's attention to the Slido to ask your questions either through the QR code or the tab in the upper left corner of your screen. And while you're doing that, I'd also like to invite you to check out our webpage, cpaess.ucar.edu, for our upcoming seminars. Our next scheduled seminar is on Wednesday, June 18th, 2025 at 11 a.m. Mountain Time, and we'll be with one of our NASA Jack Eddy postdoctoral fellows, Dr. Peijin Zhang. And so we'd like to invite you to find Robert's talk and past talks on the CPAESS YouTube channel also. And Slido is populating with questions.
Our first question is from Dr. Nick Gross. For reconstructions of features such as the polar coronal holes, given the observational limitations in that region, how confident can you be that the reconstruction has any validity?
That's a great question, and it's a question that I get quite frequently. So I was cutting this a bit short here. But we did actually a full pre-study with only using simulated or synthetic UV observations. And we only placed observers in the ecliptic plane. So very similar to this approach that we have. And what we have obtained is a very good reconstruction of the poles, even for this limiting factor. So of course we obtain higher fidelity reconstructions when we are at lower latitudes. But even for the simplified case, or for the synthetic case that we examined, we obtained good reconstructions, valid reconstructions of the polar regions only based on the ecliptic plane, based on observations from the ecliptic plane. I think the important aspect here is when we also look at this in terms of what we incorporate in terms of observations. that we have like an actual full scan of the sun by using this temporal evolution, which gives us much more information, plus having like a slightly inclined rotation of the sun, which gives us a better scan of the polar regions. So the short summary is, of course, it's an estimation, and it would be better to have actual observations, but in the absence of it, we can use this as a first approximation to obtain these observations. And it's also worth noting here that we were using like an ideal scenario. So probably we can't do this on a regular basis, because we were using here this constellation of the 3 satellites where we had like an exact spacing around the sun. So we have like a full coverage from 3 different angles by using these simulations simultaneously. I hope this is kind of clear. Yeah.
Well, as you can see his responses, I would also like to say that this was a nice talk and represents a tremendous amount of work.
Thank you. Glad to hear.
We have another one. Amazing work, Robert. Thanks for the great talk and all the best. That was from Mohammed Nadel. I hope I pronounced your name properly.
Thank you.
And then we have, what innovations are you hoping to utilize in the future to improve results even further? Maggie.
Right, yeah. Yeah, I think there are 2 paths forward. Like I think that the more challenging part, or like challenging part forward, is to advance forward to more complex physical models. So far we have applied this for ray tracing, and we have applied this to magnetic field extrapolations, which are relatively simple in terms of the physics that goes in. So what we're currently working on is also to advance this forward to full magnetohydrodynamic simulations. So those were, like, especially in the community, those simulations are extremely successful. And there are years of or decades of expertise and work that went into these simulations. So it's definitely a big challenge to catch up with those simulations. But I think there's a big advantage by trying to do this also with physics-informed neural networks, because we have this aspect of incorporating data in a more smooth way and in a more stable way. I think that's the big innovation that I'm looking forward to, is to advance this forward to more to more physically advanced models, and then also to couple this with more observational constraints, which is currently not possible with purely self-consistent simulations. So this is like the one part, and the second part would be, of course, like the easier way would be to use the existing models that we already have and try to advance this forward with more observational constraints. So for example, what we are doing for the 3D reconstructions here, for the tomographic reconstructions, is to use additional observational constraints. So we're still trying to solve a very similar problem in terms of this ray tracing, but we try to incorporate as much information as possible to advance this forward.
Thank you. I have a quick question for you, and while we're waiting in case somebody else has one. As a non-scientist, first of all, this is so amazing how you can take some observational data and extrapolate all of this information. It's fascinating. But my question is, are there certain aspects of what AI comes up with, or what your model comes up with, that are more accurate? Like, are your filament or your coronal holes, are some aspects more accurate than others? And if so, do you have any notion as to why?
Mm-hmm. Yeah, I mean, they're definitely more complex regions to fit, especially for those for the 3D reconstructions. I can show an example here as well. So for example, like filament channels are complex itself because it's like dense plasma that is suspended in the solar atmosphere. So it makes it challenging that the model learns that this is not just like a dark spot, but this is actually like a suspended absorbing plasma, like plasma in the solar atmosphere. So of course there are more challenging and less challenging regions, for example. So it's also like, for example, coronal holes are typically relatively easy to reconstruct because they have a good temporal stability. So this is basically where we get the primary advantage of this approach, is by using this additional temporal evolution in the sequence. When we have more static features, it's much easier to reconstruct them than having more dynamic features. So while we are still able to extract coronal mass ejections from this, it becomes more and more challenging, and we need to play more and more with the code to actually have it first in a good setting, and then basically perform this reconstruction specifically for a very dynamic event in it. So those are definitely, especially like those more dynamic evolutions, are more tricky to fit rather than the more static evolution. But the good part about it is that the solar atmosphere is like most parts of it are mostly static and only evolve like in a short amount of time rapidly.
That makes perfect sense. Thank you very much. We have another question from Pratik Mayank. Can this neural radiance fields approach be used to estimate the 3D CME structure from multiple viewpoints? And also any potential caveats?
That's a great question. Thank you for asking that. It's basically what we're a study that we're working on right now. I hope we get this wrapped up soon. The easy answer is yes, and I think we can even get the full tomographic reconstructions of CMEs from white light coronagraphs from 2 viewpoints. So this is a new result that we have obtained from our reconstruction. You can see some results here. So this is like slices of the electron density. Let me just quickly explain this. This is an ecliptic slice, and those are latitudinal slices, which basically give us a full 3-dimensional image of the CME. And here are slices shown through this CME topology. So yes, we, especially for the white light coronagraphs with total brightness and polarized brightness, it should be possible to obtain valid reconstructions of CME shapes and 3-dimensional extent and dynamics only based on 2 viewpoints. It's an ongoing study. We are currently papers basically in the making, and hopefully we have the study out in soon.
Well, if we don't have any additional questions, I just want to thank you all for joining us at this UCAR.CPAESS Discovery Seminar. And remember, you can go to our website and find out about future talks at cpaess.ucar.edu. And there you'll be able to find a link to their talk after it's uploaded to the YouTube. Robert, our most sincere thanks to you for sharing your important work with us. Thank you also to Jesse Webb of the UCAR Multimedia Services for his invaluable assistance. Thank you too to Don Mullally and Alex Meyer for their work in making this Discovery seminar series possible. And I hope to see you all for our next CPAESS Discovery Seminar in June. Have a good afternoon, everyone.
Thank you, everyone.